change the resolution, you double the resolution, and see if you get an answer that's very similar. If you get a big change, you make all the cells half as big, and you get dramatically different answers, you know that you didn't have enough resolution in the first case. So that's always, I would say almost always an issue. Are you adequately resolved?
No, I know oftentimes you can just kind of like slice things away or cut out portions of your volume by symmetry if you had something that was axisymmetric or something. So did you need to include the entire sphere of the Earth, or did you just take some radial segment volume?
It's possible to impose symmetry and just do, say, half the problem to save computer time, but you limit the realism when you do that. So yes, you can do that. It's possible. If you want to get just a first idea of how the system's going to behave, you can impose symmetry that may not exist in the problem you're interested in. And
so there's risks associated with imposing symmetry where there may not actually be?
I'm not sure I'd use the term risk. There's, you realize that it's not, you're giving up some realism if you really, if there's actual asymmetry. When you impose symmetry, you're going to eliminate the asymmetry. So, okay. Now, as far as an example, this is a case that Heachin presented about 2 years ago that shows this similar calculation being done in 3D, similar to the one I showed in 2D, the runaway. He doesn't have the time scale given here, but it's a short time scale. And you see these avalanches of cold material from the surface down to the bottom of the mantle, and the cone material covering the base of the mantle here with time, and so this you get the same results in 3D, but at a huge increase in cost. So in my view, it's for a lot of issues, a lot of questions, it makes sense to do it in 2D. Make sure to get a good understanding of the physics, and then if you want more realism, you go to 3D and pay the cost. This kind of calculation can now be run on a scientific workstation. I run this case. I can run this case at the next finer resolution. This grid has 128 subdivisions of the original edge of the spherical triangle. That wired grid I showed had 32 divisions. So this thing, and I can run the 64 division case on my laptop fairly routinely. So with a little more powerful computer workstation, you can now run this case. And so I'm hoping some point soon Liberty will have a high performance computing system that can run the next finer grid, 256, which will be exciting to see. Okay. So with why is this, or how does this connect with the Earth, that type of calculation? Well, basically, it shows how the separation of the continents, opening of the Atlantic Ocean, all of that could have occurred, did occur in just a few weeks' time during the flood, not over millions of years. as the current scientific establishment claims. So, and just going back historically, a major discovery occurred in the 1960s with various techniques in characterizing, especially the sediments on the seafloor. It was found that all the ocean floor on the Earth is younger than a major part of the fossil-bearing sediment record on the continents. If the sediment record on the continents is a record of the flood, of the animals that perished during the flood, that means that a staggering amount of seafloor spreading took place during the flood. And so I recognized this in the spring of 1978, and I realized this was so important, so significant. I ended up leaving the Christian ministry I was in and to go to graduate school at UCLA and get a PhD in earth science. And that's where I did my PhD at Los Alamos and developed this code that's now named Terra and still used 40 years later in various research institutions around the world. Okay. All right, let's look at a little history of the finite element method. These are just some highlights that Mark put together. There was a paper published back in 1954, and it used the terminology direct stiffness method and introduced a matrix formulation of the problems that appeared in this journal, Aircraft Engineering. Energy theorems and structural analysis. So the term energy theorems tips off the fact that they were using basically the weak form that we're going to talk about today, and in their structure analysis. And then paper in 1956 by some people, Turner and Clow, that contributed quite a bit later, stiffness and deflection analysis of complex structures, again being applied in the aeronautical realm to airplanes. And it's this paper that the first use of the term finite element method appears. And then by 1968, a decade later, finite element analysis was well underway. These are some of the authors. They were talking about curved isoperimetric quadrilateral elements for finite element analysis. And then this next paper, finite element formulation for problems of large strain and large displacements, appeared in the International Journal of Solid Structures. In this paper, it was the first elastic plastic formulation applicable to deformations of arbitrary magnitude and using spin invariant constitutive updating. So